In this lesson, we will be dealing with chemical bonding and structures of molecule. Chemical bonding and structures of molecule. This is a brief revision for learners. So we will be taking from metallic bond to ionic bond, from ionic bond to covalent bond. Covalent bond, we will go to coordinate or dative covalent bond. Then we'll now go into the different four types of structures in molecules. So let's go straight away to metallic bonds. What is a metallic bond? A metallic bond, this is the electrostatic force of attraction. It is the electrostatic force of attraction between the positively charged ions and the negatively charged delocalized electrons, or what you say delocalized sea of electrons. Remember, as I told you, the atom is positively charged. It has a positive nucleus. The atom has a positive nucleus. Why do I say it has a positive nucleus? In the nucleus of the atom, we have the proton and the neutrons. But neutrons have no charge. Only the protons are positively charged. So they carry the day. The charge of the protons give the nucleus the positive charge. And these are, around outside the nucleus are this sea of electrons in an atom. They are sea of delocalized electrons. Remember, electrons are negatively charged. So this sea of delocalized electrons outside the nucleus of the atom are attracted to the nucleus. And when these sea of electrons are attracted, these delocalized sea of electrons outside the nucleus of the atom are attracted to the nucleus, what happens? There is what we call an electrostatic force of attraction between the two oppositely charged ions. And that is what gives rise to the metallic bond. It is what gives rise to the metallic bond. A metallic bond occurs or takes place only in metals. There are some other factors that can influence the strength of the bond. For instance, the number of electrons in the sea of the localized electrons. The number of electrons in that sea of the localized electrons will influence the strength. What am I saying? I'm saying that the more the localized electrons, the stronger the bond. For instance, metals like sodium that have more delocalized electrons than sodium. Metals like magnesium that have more delocalized electrons than sodium atom. You will realize that because magnesium has more delocalized electrons than the sodium atom, that makes more attraction. There's more electrostatic attraction, and the more the electrostatic attraction, the stronger the bond, and the stronger the bond, that one makes magnesium atom to be more stronger than sodium. Magnesium atom has a higher melting point and a boiling point than the sodium atom because they have higher or more delocalized electrons than sodium. And the size of the atom too is another factor. The smaller the size of the metal, the stronger the metallic bond. So we are saying that metals with smaller sizes are stronger than metals with larger ones. Uh, um, um, what does it mean by this? You know that the distance from the nucleus, from the positively charged nucleus to the outermost shell, or to the outermost shell where the electrons are located, the distance too has an influence. The smaller the atomic size, the shorter the distance. And the shorter the distance between the nucleus and the outer electrons, outer the localized electrons, what happens? The stronger the force. But the longer the distance between the nucleus and the outer the localized sea of electrons, the weaker the force of attraction. So smaller atoms, smaller metals, metal atoms are more stronger than larger ones. But it should be noted that metals are solid at room temperature because more energy is needed to overcome the strong metallic bond. Metals are also good conductor of electricity and the heat because of the strong force of attraction. Because of the strong force of attraction. Metals are malleable. Metals are malleable and are ductile. Why do I say so? The layers of ions can slide over each other. The layers of ions can slide over each other, and for that reason, they can also be changed into different shapes. Generally, you should know that because of this strong electrostatic force of attraction between oppositely charged between the positive nucleus and the delocalized sea of electrons in metals, it gives metal generally high melting point and high boiling points. Metals also have high density. Metals, they also have high density. Now, it will take us to, you look at the diagram of metals, you'll see that the metals here, this is an atom, the nucleus is positive, and outside the atom you have the localized sea of electrons. So the delocalized sea of electrons here, which are negatively charged, are attracted to the nucleus. That's what gives the metal the strong charge, the strong force of attraction, and make it to be strong. It takes us now to the second type of bond, which is the ionic bond. What is an ionic bond? Remember, ionic bond, the word ionic, it has to do with ions. It shows that ionic bond occurs only between metals and non-metals. It occurs between metals and non-metals. Between metals and non-metals. Occur between metals and non-metals. And secondly, you will see that metals are usually those in group 1 and group 2 and group 3. So it occurs between metals and non-metals. The metals are mostly those of group 1 that will give electrons, those of group 2 that will also give their electrons, and those of group 3 that will give their outer electrons. And metals of group 1, they have only one electron in their outermost shell. Metals of group 2, they have 2 electrons in the outermost shell, and metals of group 3, they have 3 electrons in the outermost shell. These are the electrons that are used in the bonding. These are the electrons that are used in the ionic bonding for the transfer. And precisely, we can say an ionic bond is the electrostatic force of attraction between oppositely charged ions formed by complete transfer complete transfer of electron from one atom, usually the metals, to another, usually the non-metal. The essential word there is electrostatic force of attraction between oppositely charged ions, formed by what? Complete transfer of electrons. Complete transfer of electrons from one atom, and usually the metal, to another atom, which is the non-metal. It should also be noted that metals, they lose electron to be what? To be cation. They give out the electrons to be cations. Most metals, they give out electrons to be cations. In this case, when they give out the electrons, they become cations. The non-metals, they give out electrons. Oh. Metal give out electrons. They give out electrons to be what? They give out electrons to become. They give out electrons to become cations. To become cations. It should also be noted that the non-metals accept the electron to become anion. The non-metals accept electrons to become anions. The anions. Then it should also be noted that cations and the cations and the anion are then attracted by a strong electrostatic force. Cations plus anions are attracted by a strong electrostatic force. By a strong electrostatic force, attracted by a strong electrostatic force. Okay. We should know that it should be also remember that this compound, any compound from this type of bond, is called an ionic compound. For example, we are talking an example of sodium ion and chloride ion. Sodium chloride. That is an example of it. Any compound formed between the cation and the anion is an ionic compound. And we can say that then the attraction between the anions, and the neighboring cation, if an anion is attracted to a neighboring cation and vice versa, it will result in a huge ionic lattice. A huge ionic lattice when the anions are attracted to a neighboring cation, and this other cation is attracted to a neighboring anion. This results in a huge lattice structure that is being formed. And that's why we say sodium chloride can form a lattice structure. What is a lattice structure? A lattice structure is this is a regular or repeated arrangement. It's a regular or a repeated arrangement of particles, usually ions, that are present in a solid. They have a particular pattern that appear. They are arranged in a particular pattern. All these ions are arranged in a particular pattern in a solid. So we say these are repeated arrangement. They have a repeated arrangement of the ions in a solid. Another example of this complete transfer of sodium chloride, as we said here. Sodium is a metal, chlorine is a non-metal. Now, in the outer electrons, sodium has only one electron. It belongs to group 1 of the periodic table. The outer electron of chlorine, there are 7 electrons there. We have 1, 2, 3, 4, 5, 6, 7. The main aim of this ionic bond, the complete transfer of electron from one atom to the other, is that they need a stable structure. At this level, sodium atom is not stable. Chlorine atom is not stable. Why? For an atom to be stable, it must have at least 2 electrons or 8 electrons in its outermost shell. But in this case, sodium has only 1 electron in the outermost shell, so it is unstable. And chlorine has 7 electrons in the outermost shell, it is unstable. For that reason, something must be done so that they can achieve an octet of electron. An octet of electron, or a complete octet of the outermost shell. For that purpose, sodium will have to give out electrons. Sodium will have to give out electrons to chlorine. This electron to chlorine. And when it gives out the electron, it comes back to its normal 2 shape, which is, when it gives out the electron, it will come back to 2, 8. But this chlorine atom, when it accepts this electron, when it gains this 1 electron, it completes the octet. It completes the octet by moving to what? By moving to 2, 8, 7. So the main objective of this is that the atoms, they achieve a complete octet of the outermost shell electrons. Then secondly, all this, the metals that give out the electron will achieve a positive charge. The non-metals will achieve a negative charge. And this is how it is represented. Another example of this is the formation of magnesium ion. The formation of magnesium ion, which is magnesium ion will be like this one. Formation of magnesium ion and oxide ion by electron transfer. So we have magnesium. This is magnesium. Magnesium has 2 electrons in the outermost shell. It is here. Let me put it here. Magnesium is here. There is magnesium. Now it has 2 electrons. Magnesium has 2 electrons. Oxygen has this oxygen here. Oxygen has 6 electrons. We have 1, 2, 3, 4, 5, 6 for the oxygen. So now, what is happening here is this. Let me represent this with yellow. So what happens now is that there is a complete transfer of electron. The complete transfer of electron is from what? Magnesium will have to give these electrons here, and this other one here. And the result is what? These are electrons. Here initially, magnesium has what? Magnesium has initially, it is 2, 8, 2, 8 what? 2, 8, 2. Oxygen has 2, oxygen has 2, 6. 1, 2, 3, 4. Yeah, oxygen has 2, 6. So for this to be complete, what happens? Magnesium now, when it drops this one, it will be magnesium will be, there is magnesium 2 plus, 2 electrons have been lost. It will be magnesium, which is 2, 8. Then oxygen. Oxygen has gained 2 electrons. 2 electrons. So what is the oxygen now? There is 2 oxygen here. Oxygen will be, it will fill its shell now to what? To 8. It will be 2, 8. That will be oxygen now. From 282, magnesium from 282 to what? To 2, 28. Oxygen from 26, to what? To 28. And what happens in the structure? The structure now becomes, what happened in the structure? Now magnesium will be there and oxygen will also be there. We'll gain 2 ions. So that is how the whole thing will be. This one will be this one, and this will be this. So summarizingly, we are saying that it involves a complete transfer of electron from one atom to the other. The one that transfers the electron acquires a positive charge. The one that takes the electron acquires a negative charge. The overall goal is that this one has a complete octet of electrons in the outermost shell, and this one and the anion too also has a complete octet of electrons in the outermost shell. Another example is that of calcium chloride. Calcium chloride does the same thing. Calcium has atomic number of 20. It has an atomic number of 20. 2, 8. It has that's 10, 18, 20. From these 20, there are 2 electrons in the outer shell. The 2 electrons in the outer shell, it makes calcium unstable. So it needs to give out these 2 electrons to be stable. Chlorine, on the other hand, has 7 electrons. It makes chlorine unstable. So what happens? Chlorine needs another electron so that what it can fill the outermost shell to be 8 so that it becomes stable. So what happens? Electrons are transferred here. Electrons are transferred here. Electrons will move here. Electrons will move here in this direction. Electrons are transferred to chlorine, and another electron here is transferred to this other to this chlorine. That is how the whole thing goes. 2 chlorine atoms are involved in this. Now, the sodium and the calcium atom that has lost 2 electrons acquire a charge of +2. Now, from here, the electronic configuration from 2882 moves to what? The electronic configuration from 2882 moves to what? It moves to 288 because 2 electrons have been removed. Now, the 2 chlorine atoms, the chlorine atoms that accept the electron acquires a negative charge. There's an increase in the number of electrons this time around. The one that accepts electron acquires a negative charge. There is an increase in the number of electrons this time around. For that purpose, chlorine that has an octet, that has an electronic configuration of 287 will not go to what? Will not go to 288 because this one has gained 1 electron to fill the shell, and this other one has also gained 1 electron to fill the shell. That is how the whole thing is. Now it moves us from ionic bond to what we'll call covalent bond. A covalent bond, as you see, These are a good example of covalent bonds. A covalent bond using a dot and cross diagram to represent the formation of covalent bond in oxygen. Oxygen has 8 protons, implying that oxygen has 8 electrons. The first shell of oxygen will occupy the first 2 electrons. The next shell will have 6 electrons. As I told you, with 6 electrons, it is unstable. It makes the atom to be unstable. So oxygen will need to bond with another oxygen. It will need to bond with another oxygen. But for bonding to occur, for covalent bond to occur, what must happen? The first thing is, 1, the covalent bond will occur mostly between nonmetals. Occurs mostly between nonmetals. That's what happened with covalent bond. Then, now, what is a covalent bond? A covalent bond, it occurs between nonmetals. And between what? Between the positively charged nuclei of the atoms and the lone pair of electron and the bonded pair of electron. Take for instance, we have, this is an atom, this is another atom here. Okay, these atoms are positively, they have the positive charge nuclei. This one, they have a positive nucleus, yeah. So now, what happens here? Now, we have electrons here. Let me say these are electrons. These are electrons. From here to this place, and again from here, this nucleus to this other one. That is what is happening there. We can now say a covalent bond is the electrostatic force of attraction between the nuclei of 2 atoms. This is an electrostatic force of attraction between the nuclei of 2 atoms and a shared pair of electrons. These are the nuclei of 2 atoms. These are the nuclei of 2 atoms that are positively charged. The nuclei of 2 atoms. So now, the force of attraction between the nuclei and the shared pair of electron, the force of attraction between the nuclei and the shared pair of electron here is what we call the covalent bond. Once more, the covalent bond is the electrostatic force of attraction between the nuclei of 2 atoms and a shared pair of electrons. So, in covalent bond, let's go back again. In covalent bond, it occurs mostly between nonmetals. Secondly, it involves sharing of electrons. Sharing of electrons. Sharing of electron pair. It involves the sharing of electron pair. Then the atom that provides excuse me. Then I said it occurs between nonmetals. It involves sharing of electrons, and each atom in the bond acquires what? It acquires a complete octet of outer electrons. Then a shared pair of electron result in what? If it is a shared pair of electron, any shared pair of electron will result in what? Will result in a single bond. Any if there are 2 pair of shared electrons, if we have 2 pair of shared electron, If there are two pair of shared electrons, it result in what? It result in what? It result in double bond. If there are three pair of shared electrons, it result in what? It result in triple bond. So any single pair of shared electron, if it is a single shared, if a pair of electron is shared, if a pair of electron is shared, it result in a single bond. If two pairs of electrons are shared, it result in a double bond. If three pairs of electrons are shared, it result in a triple bond. So in this case of oxygen atom, there's an oxygen atom here, there's another oxygen atom here. See how they share the electrons. Now, they need to acquire an outer octet of a complete octet of electrons, so they need to share. This electron, one atom will one of the atoms will contribute 2 electrons for the pairing. And what happens? This one is here, this is the pairing here, this is another one here. This pairing here, there are 2 pairs of electrons and it results in a double bond. So if we look around, atom 1, the atom 1 of oxygen, it has how many electrons? 1, 2, 3, 4, 5, 6, 7, 8. It has an octet now. Atom 2, it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons. Therefore, we say that each atom in the bond acquires an octet of acquires a complete octet of electrons. Then let's go to another one of sodium molecule. Okay, a sodium molecule here, as I said, sodium has only 1 electron in the outer shell. I mean, 7 electrons in the outermost shell. And it is unstable and it needs to complete it to octet. So the 2 sodium atoms will come together. The 2 atoms of sodium one will have this. This is one of chlorine. Sorry, 2 atoms of chlorine. Sorry, please. 1, 2. Yeah, these are the 2 atoms of chlorine. There is one here. So now the other one will do what? 1, 2, 3, 4, 5, 6, 7. So when they come together, what becomes of them? The one has what? It had this chlorine and a chlorine, and the one has 1, 2, 3, 4, 5, 6, and 7. The one has 1, 2, 3, 4, 5, 6, and 7. Now each of them now has 8 electrons in its outermost shell. All of them now have the same number of they still have the same number of electrons. We have 2, 8, 2, 8, 7. It has 2, 8, 7. It has 2, 8, 7. And this other one has 2, 8, 7. 2, 8, 7, 2, 8, 7. But because in order to complete it, they cannot transfer electrons, so they will need one of the electrons. This electron here is the one that goes into the sharing. They share it. All of them, they share this one, and that's what gives the chlorine that structure like that. They share this, and that gives chlorine that. So these electrons, these are the electrons that are going in for the pairing. And that is how you can have a chlorine molecule. That is a chlorine plus a chlorine gives a chlorine molecule. This chlorine, yeah. Chlorine plus chlorine will give you the chlorine molecule there. Okay, let's go another example of the one that can give you a double bond again. Dot and cross diagram to represent an ethene molecule. An ethene molecule, this is it, we have 4 atoms of hydrogen. Hydrogen has only one proton. It has only one proton. In that case, and one electron. In that case, it's only one of the electrons. Because of it, nitrogen is unstable. I mean, hydrogen is unstable. Because hydrogen has only one electron, it is really unstable. It needs to have at least 2 electrons in the outer shell for it to be stable. And for it to do it, it cannot give out all the electrons. It will look the possible means to share the electron. If it shares the electron, then that will be okay. So in that case, the 2 carbons will come together and share. These are the 2 carbons. They will come together and share. They will share, come together, share the electrons. Then the hydrogen will attach themselves there. So 2 hydrogen will go with this one. This 2 hydrogen will go to 1 carbon, and the 2 hydrogen will go to this carbon too. And when they go to the carbon, then the carbon themselves, they will do what? The carbon themselves will have to do what? Will have to come together, resulting in this. So that is what happens. And when a double, we said when 2 pairs of electrons are shared, it results in a double bond. And only 1 pair results in a single bond. If there are 3 pairs, it results in a triple bond. So this gives the structure of a ethene molecule. Now, the simplest one is that of hydrogen, and that of methane. Dot and cross diagram to show the formation of a methane molecule. Excuse me. This is a methane molecule. There are 4 atoms of hydrogen here. There are 4 atoms of hydrogen here. If we were to write the equation, we will have hydrogen. We will say hydrogen plus carbon to give methane. And we need to balance our hydrogen. So what is happening here? We have 4 atoms of hydrogen reacting with 1 atom of carbon. Carbon has an atomic number of 6. In the first share, it has 2 electrons. The second share, it has 4 electrons. This electron makes carbon to be unstable. So carbon will undergo what we call bonding with hydrogen atom. By doing this, it will undergo with bonding with hydrogen atom. And this type of bonding is the covalent, a covalent bond, sharing of a pair of electrons, where each of the atom will donate an electron for the pairing. Carbon gives an electron, hydrogen gives an electron, a pair of electrons is established. They share. And that results in what? It also results in this structure we call methane. It results in methane. So now there is another type of covalent bond. There's another type of covalent bond, we call it dative covalent bond, or what we call coordinate bonding. Coordinate bonding. For dative covalent bonds, these are bonds. Dative covalent bonds are bonds that only one of the atom will give the electrons. One of the atom provides electrons for the pairing. Once more, this is a bond formed. This is a bond. This dative covalent bond or coordinate bond is a bond formed when one of the atoms provides both electrons for the sharing. The pair of electrons that is used for the sharing is donated by only one atom. Two of the atoms are not donating the electron as in the other cases. In this case, only one of the atoms will give the pair of electrons for sharing. And for an atom to provide a pair of electrons for sharing, it must have a lone pair of electrons on itself, on the atom. There must be a lone pair of electrons on the outermost shell for that atom to donate an electron for sharing. And during this bonding, there is an arrow indicating or showing the direction of the movement of the lone pair of electron. For example, nitrogen has a lone pair of electron. That's one condition. The atom must have a lone pair of electron on its outermost shell. Secondly, there is an arrow to show the direction of the movement of the electron. So there must be an arrow to show that this electron is being donated to hydrogen. The hydrogen ion, the hydrogen ion here in this ammonium, an ammonium molecule. This is an ammonium molecule. In an ammonium molecule, the hydrogen, there is ammonia and the hydrogen ion. The ammonia there has no electron again. It is bare. It has no electron again there. So the only thing for it to stabilize itself is that it needs to attach itself. It's a proton pair acceptor. It will accept a pair of electrons. An ammonia is a proton. An ammonia is an electron pair donor. Meanwhile, this proton here or this hydrogen ion here is an electron pair acceptor. So in that case, there is a coordinate bond that is being established. Nitrogen donates a lone pair of electron to the hydrogen ion. And what happens? This is it here. Now, hydrogen is now stable because it now has at least two electrons in its outer shell. Now, nitrogen 2 is now stable. Nitrogen now 2 is still stable. So, as I said, the lone pair of the arrow shows that a lone pair of electron was donated for the pairing by nitrogen. That is why it is indicated here like that. It indicates that a lone pair of electron from here was donated to hydrogen ion. Another example of coordinate bonding or dative covalent bond is the one that has to do with aluminum chloride dimer. In aluminum chloride, the central atom here, which contains aluminum, has only 6 electrons. It is unstable. It needs 8 electrons. So it's lack of a pair of electrons. Here too, it is also lack of a pair of electrons. So what happens now is the chlorine atom here with this pair of electron will have to donate it to what? This pair of electron here. The lone pair of electron here will have to go this way. There will be a bond here. Then, here too, see what is also happening. On this other. See, the lone pair will go here, and it is indicated by what? By the arrow. Now, on this other side here, there is chlorine here. This chlorine has a lone pair of electron here. There is a lone pair of electron here. Chlorine. So what must chlorine do? In order to stabilize this aluminum, it need to donate this alone pair of electron to aluminum. So it goes in this direction. Let me use this one. So it goes in this direction. So in that case, you will see that the lone pair of electron has been donated here by chlorine. Here, this is it. And on the other hand, the other one here was donated here by this other one too. You now see how the whole thing is moving. And I said the arrow from the structure, the arrow will indicate the movement. This arrow here, movement of electrons. These are electrons, are movement of electrons. It indicating the movement of electrons. Now, out of the formation of the aluminum chloride dimer through two dative covalent bonds, there are two dative covalent bonds. First one here, this is the first dative covalent bond, and this is the second dative covalent bond. So there are two dative covalent bonds that have been formed here. So there are two dative covalent bonds, as I said, this is one, and this is two that have been formed. Okay, there's another structure we call octet deficient and octet expanded species. There are some structures, since the ultimate goal for sharing of electron or covalent bonding is that the atom, each atom acquires a full outer octet of electron. But in this situation, there are some species that are deficient of it. For example, boron trifluoride. This is an only exception where the central atom has less number of electrons, less than 8 electrons. 1, 2, 3, 4, 5, 6. Those are exceptions. Then there's another exception, we call it expanded octet. That is, the central atom has more than 8 electrons. In this case, it is phosphorus pentachloride. 1, 2, 3, 4, 5. Phosphorus pentachloride. Where phosphorus, the central atom has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the only exceptions. Now, it takes us to the types of structures. Types of structure, there are about 4 types of structures. 4 types of structures that exist in solids. We have the giant ionic structure, giant molecular structure, giant metallic structure, simple molecular structure. What are these structures? From the bonding that we have discussed, based on the bonding nature we have discussed, beginning from metallic bond to this stage, we can devise the type of structure that these molecules can form. The types of molecules that can form this type of structure. We will be starting with a giant ionic structure. We just discussed that. For giant ionic structure, an example of a giant ionic structure is, I just discussed it under bonding, is an example of it is sodium chloride lattice. An example is sodium chloride lattice. That is an example of that type of structure, sodium chloride lattice. And in the sodium chloride lattice, this is an example of it here. I told you that a sodium chloride lattice, there is a regular or repeated arrangement of ions in the solid. Repeated arrangement. You see that there's a pattern that is following from there's a particular pattern for chlorine. Look at the chlorine. chloride in this line. Look at the sodium. Look at the sodium ion. So I said a lattice is a regular or a repeated arrangement of ions or particles in a solid, and it shows it here. So this is a good structure of an ionic lattice, which is sodium chloride. And what are the type of particles that are present here? Of course, the type of particles present in this lattice are ions. They are positively charged and negatively charged ions. They are ions, positively charged, positively and negatively charged ions. They are positively, negatively charged ions. They are positively and negatively charged ions. Okay, what is the type of bonding here? As we have been saying, any bond between negatively charged ions is what we call an electrostatic force of attraction. So we say the bond, there is the type of bond present here is a strong electrostatic force of attraction between oppositely charged ion, resulting in this ionic lattice. A strong electrostatic force of attraction between oppositely charged ions, resulting in an ionic bond or ionic lattice. Well, what about the solubility of this structure, of this giant ionic structure? The solubility, well, they are soluble in water. Most of them, like sodium chloride, most of them are soluble in water. They are soluble in water. They are soluble in water. About their melting point, excuse me, about their melting point, you know that because there's a strong electrostatic force of attraction between the oppositely charged ions, they have a very high melting and the boiling points. They have high melting points and boiling points. Okay, about their conductivity of electricity. Um, for ionic compounds, ionic compound will only conduct electricity when molten or when dissolved in water. They conduct electricity in molten, conduct when molten, conduct electricity when molten or dissolved in water. Or dissolved in water. Then about the ability of malleability and ductility. Metals, sodium chloride lattice, they are not malleable, they are not ductile because their ions cannot slide over each other. They are not malleable or ductile. Not ductile, not malleable, malleable, or ductile. Okay, that is what you can have about this type of structure resulting this giant ionic structure. Our example was sodium chloride. It moves on to the next type of structure, which is giant molecular or giant covalent structure. Giant molecular or giant covalent structure. We have examples, many examples of this. We have diamond, we have graphite, and we have silicon dioxide. This is graphite. Here is graphite. This an example is a structure of graphite. This is diamond. And this is silicon dioxide. And that is silicon dioxide. From their structure, you will see their structure very well. Silicon, you see the layers of the in graphite. Graphite is bonded to 3 electrons, and one of the electron. Graphite is bonded to 3 electrons, and one of the electrons is delocalized, and that makes graphite a good conductor of electricity. But this one is bonded to 4 different electrons. In diamond, the carbon atom is bonded to 4 different electrons. We have 1, 2, 3, 4. They are bonded to 4 different electrons. So, example, we said the example in this type of structure, we have graphite, we have diamond, we have silicon dioxide. But what are the type of particles present here? We cannot be talking of ions. There are not ions here. We can't talk of ions. So the type of particles that are present in this type, in making this type of bond here, or this type of structure, are atoms. The particles present are atoms. Atoms are present. So the particles present here are atoms only. Then, okay, what type of bonding is occurring in this molecule, in this giant molecular structure? What type of bond do you expect to see here? The type of bond that you can expect to see in a giant molecular structure, a giant covalent structure, there are strong covalent bonds between atoms. Between atoms, we can only see covalent bonds. We just treated covalent bonds. So between atoms, what we can observe are there are only atoms that are sharing electrons. They contribute electrons for sharing. So in that case, the type of bonding occurring here is covalent bond between atoms. But the type of covalent bond here, there are strong covalent bonds between atoms. Strong covalent bonds. Strong covalent bonds. Then about their solubility in water. Of course, they are really insoluble in water. They are insoluble in water. They are insoluble in water. And if we want to talk about their melting point, since there are strong covalent bonds, what happens is that they will have high melting point. Like graphite, I mean like a diamond and the silicon dioxide, they will have high melting point and a boiling point. They will have high melting point and boiling point because they have strong covalent bonds. Then about their conductivity. In conductivity here, I said graphite is bonded to three electrons. One electron in graphite is delocalized, and that one causes graphite to be a good conductor of electricity. But for diamond and silicon dioxide, they are non-conductor of electricity because they don't have mobile electrons. And finally, their malleability and ductility. Of course, they don't conduct electricity. They don't have mobile electrons, mobile sea of electrons. In that case, they are non-malleable. They are non-malleable and non-ductile. It takes us to giant metallic structure. Another structure is the giant metallic structure that we just treated in bonding. In giant metallic structure, you will see that as we said, here it involves this is an electrostatic force of attraction between the positively charged nucleus and the delocalized sea of electrons. In this case, see the order in which the atoms are arranged. the atoms are arranged in this order, you can realize that the atoms can slide, the ions can slide over each other from this. The ions can slide over each other. The ions can slide over each other. And because they can slide over each other, that is why we say they are malleable and they are ductile. Therefore, we can say an example of the, let's start away, an example of such a giant metallic structure. We can take a copper metal. A copper metal is an example. A copper metal. A copper metal is an example of it. And the particle present here, as you saw it, they are ions. They are ions. They are ions. They are ions. And these ions are what? They positively charged, the positive ions, and the mobile sea of electrons, which are also the negatively charged ions. So we have positive ions and the mobile sea of the localized electrons that are here. And what is the type of bonding that is occurring here? The type of bonding that is occurring here is a strong metallic bond formed when the positive ions formed between the positive ions and the delocalized sea of electrons. And because of the, it gives this structure is a strong structure. The structure is strong. And because of the strength of the structure, what happens to the boiling point? They will have high melting point and high boiling point. Why? They require they will require a lot of energy to overcome the strong electrostatic force of attraction. For conductivity, they are good conductor when they are solids because of the mobile electrons in them. And as I said, malleability and ductility, they are malleable and they are also ductile because because the positively charged ions can slide over each other. The positively charged ion can slide over each other. And that takes us to the last section of our lesson today, the simple molecular structure. Simple molecular structure, an example of a simple molecular structure is iodine. Iodine molecule. You know, iodine molecule will only undergo, they will only undergo a covalent bond. It's a covalent bond that will undergo between iodine and this other iodine molecule. So when an iodine molecule undergoes this type of covalent bond, in between them there is a force of attraction. We call it the force of attraction between iodine molecule is intermolecular forces. Intermolecular forces are the forces in between the molecules. These are intermolecular forces between the iodine molecules. And because of the weak intermolecular forces, these are weak intermolecular forces. They are weak. They are weak intermolecular forces. These are weak intermolecular forces, or what we call van der Waals forces. Van der Waals forces. These are weak intermolecular forces or weak van der Waals forces. And because of the weak van der Waals forces, it makes them, their boiling point and their melting point, they have low melting and boiling point because the intermolecular forces are weak and can break when it melts or when it boils. They are non-conductor of electricity. They are also non-malleable or ductile. About their solubility in water, they are really insoluble. Quite often they are really insoluble. So the only force here is the intermolecular forces between the molecules. And these are weak forces between molecules. They can easily break when they are heated. So that is all for the structures. So thank you for listening. You have to share, like, and subscribe for more of our tutorial lessons.